Hello everyone and welcome to the video on logistic regression. In our most recent video we talked about binary linear classification, which is a method if you get a bunch of data points and you want to assign them into two classes, then you can train a model such that if you get a new data point you can predict which class you think it's going to be in. But this is a discrete classifier, so it either puts it in one class or the other class, but we might want our model to have a little bit more nuance and to be able to say, oh, there's a 40% chance that it'll be in the first class, or, oh, we think there's like a 73% chance that it'll be in the first class. So today we're going to develop a model that can do that. So we're going to continue with our linear model, our WTX, but the problem is that for a data point, WTX just gives us some number. It does not actually give us a probability. So we're going to use the sigmoid function, which takes in input z and then just gives us 1 over 1 plus e to the negative z. And that's really convenient because 1, it gives us a value between 0 and 1. It can give us any of those values, but it's always between 0 and 1, which means it's going to be a probability. And also it's differentiable, which is really nice because we're probably going to need to take some gradients in our process of optimizing or finding the best w, and so that's a convenient property of the function. So our model will take our linear model, WTX, and we'll plug it into our sigmoid function. So I'm going to start with a binary classifier, but I'll talk about later in this video how to extend it to more classes. So we take our linear model, we plug it into the sigmoid function, and that gives us the probability that the data point x is in the first class. Since there are only two classes, the probability that's in the second class is just 1 minus the probability that it's in the first class.
So now we want to find the best w. And this probably shouldn't say we'll use MLE. The approach will sort of start like MLE, but then instead of maximizing the likelihood, we'll end up minimizing the negative log likelihood, and then we'll realize there isn't a closed form solution, so we'll use gradient descent, which is a technique we introduced in a previous video as a numerical approximation.
So first we need to write out the likelihood. So we want the probability of getting our data y, given that w is our true coefficients vector. So we're going to assume that all the data points are independent, which is to say that the probability of the likelihood for all of them is just the product of the likelihoods for each of them. And the probability that the nth point is in class 1 is just sigmoid times WTXN, and the probability that it's in class 2 is just 1 minus that. So yn is equal to 1 if it's in class 1, and yn is equal to 0 if it's in class 2. That's just how we're going to denote the data. And so we can use this sort of convenient mathematical trick where we take the probability that's in the first class and we raise it to yn, and then we take the probability that's in the second class and we raise it to 1 minus yn. So if the data is in the first class, then yn equals 0. And so, if the data is in the first class, then yn equals 1. So this will just simplify it. This second term will just be this to the 0th, which we'll end up just getting rid of because that to the 0th is just 1. And then this will be 1. And so we'll just end up with the probability that the probability of the nth point being in the first class, which is exactly what we want because yn equals 1. However, if the nth point is in the second class, then we have yn equals 0. So this will be 0. So this first term will just be 1. And then this will be 1. So we'll just end up with this probability right here, which is what our model would say is the probability that the nth point is in class 2, which is what yn equals 0 denotes. So this is sort of just a mathematical trick to make it easier to represent the likelihood. So as I said before, we're going to use the log here. Remember, anytime you have a large product of things and you don't want to deal with all of them, always take the log, especially if you're going to differentiate afterwards. It'll make everything a lot simpler. So we take the log, and then by log rules, this product turns into a sum, and then also this product right here turns into these two respective sum terms, and the exponents come down. So that's much nicer to work with. And so this gives us the log likelihood. We want, the log is a monotonic transformation, and the likelihood is something we're trying to maximize, but we want to be minimizing something, so we're just going to take the negative of it. Minimizing the negative is the same thing as maximizing the non-negativized version. And so this is what we call our objective function. Our objective function is usually the thing that we're trying to maximize or minimize. But our objective function is the negative of the log likelihood. And that's a pretty common thing to do. The log makes everything much simpler to work with and differentiate. And the negative means then you can minimize it, which is what our gradient descent technique is meant to do. So we're going to go ahead and do the math for this. So first, I'm going to do, in a little aside, I'm going to take the derivative of the sigmoid function because we'll be using this a lot. So the derivative of the sigmoid function, we're just going to write everything out. And then we have low d high minus high d low over the square of what's below, right? So you take the square of the denominator, and then the derivative of 1 is just 0, so there's no first term, and then the derivative, then we subtract the derivative of the bottom, which is negative e to the negative z, so that's just e to the negative z on the top here. And then we can just separate this out into two terms that we multiply together, and the first term we see is just the sigmoid function, and the second term is 1 minus the sigmoid function, right? Because 1 is 1 plus e to the negative z over 1 plus e to the negative z, and then we subtract the sigmoid function, so we subtract 1 from the top, and then we just get e to the negative z over 1 plus e to the negative z. So we see that the derivative of the sigmoid function is just the sigmoid function times 1 minus the sigmoid function. And so now we're ready to take the gradient of the entire thing. So let's take the gradient of the objective function with respect to w. So the first thing that we're going to do is we just apply the chain rule, and so the derivative, I'm going to take the derivative in two pieces. First I'll take the derivative of this part, and then I'll take the derivative of this second part, because that's just taking the derivative, or in this case gradient, over sums. So first we have the chain rule. From our log term we have 1 over sigma, or 1 over the sigmoid function of wtxn, and then we have the derivative of the actual sigmoid function on the inside, and that gives us this, just like we differentiated above, and then the gradient of wtxn with respect to wt, as we've discussed before, is just xn. Then we're going to take the gradient of the second part. So again, 1 over yn doesn't have any w dependence, we just pull that out. Then we take the derivative with respect to the log, and let's just make this a little smaller so you can see all the parts. Yeah, so then we take the derivative with respect to the log, and that gives us 1 over 1 minus the sigmoid function, right, 1 over the inside, and then we take the derivative of this stuff on the inside, and that gives us our leading negative, and then also just the derivative of the sigmoid function as we calculated earlier, and then the gradient of wtxn, which is just xn. So now we can do a little bit of cancellation here. First we see these two things cancel, sigmoid on the bottom, sigmoid on top, and then 1 minus sigmoid on the bottom and 1 minus sigmoid on top will cancel out. And so that gives us our equation right here. And then I've canceled out the first term that I've canceled out, and there should be a parentheses right here, is yn times sigma of wtxn times xn, and that cancels out with yn times sigma of wtxn times xn right here, right? Because this one is positive, the second one is positive, and the first one is negative, so those two cancel out, and we're left with, we can pull the xn all the way out to the front here, and then we get yn minus sigmoid of wtxn. So that gives us our gradient. Now, another way that we can write this is we can just take the negative and we go ahead and distribute the negative to just flip these around. And then we know that sigma of wtxn is actually our model's prediction, assuming w, of how likely the nth point is to be in class 1, whereas yn is the actual true probability of the nth point being in class 1. So we flip these around and we use y hat n here to denote the estimate, so our model's prediction of how likely the nth point is to be in class 1. And so this is actually a fairly interpretable gradient. So the gradient is sort of like, here it comes out to be the weighted average over all the data points, where the data points are weighted sort of by the prediction error, right? Because if our prediction for yn is really close to the true value of yn, right? If that point is in the first class and we think it's really likely to have been in the first class, then that x point is not weighted as highly. Whereas if we're really far off, then there'll be a large influence of that point on the gradient. So usually it's sort of hard to get an analytic solution or a closed form solution out of this, so we'll just use gradient descent as we talked about in the previous video. We'll just update by the learning rate times the negative gradient. Cool, so what if we use more than 2 classes? Let's say we have k classes. So now w is not just a 1 by k vector, it is a d by k vector. So, and our linear prediction is again w transpose times x, and our linear prediction gives a k by 1 resulting vector. So now we have a bunch of predictions, and again, remember we use the sigmoid function to take a linear function and transform it into probabilities. So what we really would like to have is a vector where the first thing is like the probability that the nth point is in 1, and then the second thing is the probability that the nth point is in class 2, all the way down to k classes. And so how are we going to take, we have a k by 1 vector, and each of the elements of the vector sort of is a proxy for how much we think that it might be in that class. Like if the value of the kth element of if the value of the ith element of w transpose x is higher, that probably indicates that the model thinks that it's more likely to be in that class, but we still don't have exactly probabilities. So we're going to use the softmax function. So softmax function takes in a vector z and then just applies the exponential function to each element of the z vector, and then divides all of that by the sum of all of the exponents of all the components of the vector. So this will give us a vector of probabilities. Every probability will be positive since we applied the exponential function to it. And then also all the probabilities will sum to 1 because we have this normalizing constant out in front. So this is exactly what we want. It'll transform sort of our proxy for how much we think each thing is in each class into actual probabilities that add up to 1. So we will predict, for data point xn, we'll predict softmax of wt xn, and that will give us what our model thinks is the probability that the nth point is in the first category, the second category, all the way down to the kth category. And we'll have to make a little bit of an adjustment to yn here too, because previously we said yn could either just be 0 or 1, where 1 just represented that it was in the first category. But we don't really want to use like 0, 1, 2, 3, something like that. So instead, we'll use what's called a one-hot vector. So y will be a k by 1 vector, and it'll have the ith, if y is in class I, because we're given our training data, so we know what class it actually is in, then the ith value will be 1, and everything else will be a 0. So it'll just have a 1 in the element of which it is the category. Great. So again, we're going to try and approach this with MLE, and I'd encourage you to pause the video here and see if you can work this out for yourself. Because it's similar, it's definitely a little bit more complicated than the 2-variable case, but I think it's a good exercise to go ahead and try it out. Great, so we're going to go ahead and walk through it together.
And so again, we'll start with an approach that might kind of look like MLE at the beginning, but we'll turn it into minimizing a negative log likelihood, and then use gradient descent.
So we will first write out the likelihood. And again, we're going to use sort of a similar trick where we take this exponent over here. So again, we assume the data points are independent, so we can just take the product of the individual likelihoods for the data points. And for any data point, the probability, our model's prediction of the probability that it's in the ith class is going to be just the ith element in this softmax prediction vector. And then we're going to raise it to the y sub ni. And so y sub ni is only going to be 1 for one I, right? For the true class that y is, this will be 1. And so then we'll get that term in the softmax vector. And then for everything else, y and I will be equal to 0. And so those will just be 1. So in a product, that won't change anything. So again, we're using the exponent trick here to only get the term relevant to the actual true class of y. And it's just nice to be able to write stuff like this, because this would work even if y was, say, a vector of probabilities as opposed to just a one-hot vector. So then we're going to take the negative log likelihood, just like we did previously. Negative just makes this negative appear in the front, and likelihood makes everything simpler because the products turn into sums. And now we're going to take the gradient, very similar to the two-variable case. So first, before we do anything else, we're going to do a quick mathematical aside where we take the derivative of softmax, and that will be very helpful in our final derivation. So let's say we have softmax on some vector z, and we're looking at the ith component of the softmax, and we're taking the derivative with respect to the hth component of the z vector. So the ith component of the softmax vector is just e to the zi over the sum of the exponents of all the components of the vector. And so now we apply derivative rules, right? We take the denominator and we square it, and then we put that on the bottom. And then we have two terms on the top. First, we have the derivative of the denominator times the denominator times the derivative of the numerator. So the denominator we just put here, and then the derivative of the numerator, if h is equal to I, then it will just be e to the zi, and if h is not equal to I, then e to the zi has no dependency on z sub h, so it will just be 0. So we can just use ih is the ith row h column of the identity matrix, right? So it's only 1 if I equals h. Another way to write this would be an indicator random variable that I equals h, but here we just chose to write it with the identity. And so that gives us the first term. And then we want the numerator times the derivative of the denominator. So we subtract, and then we put the numerator, and then the derivative of the denominator will just be only one of the terms in this sum will actually have h dependence, and that's exactly the term which is just e to the zh. And the derivative of e to the zh with respect to zh is just e to the zh. So we get this last term right here. So now let's break this up a bit. The first thing we're going to do is we're going to pull out the zi from both of these, and we're also going to pull out one of the sums on the bottom, and that'll give us this first term right here. And then we just write the second part over here. Great. So we realize that this first term is actually just softmax of z, the ith element of the softmax of z. And then this second term right here, we actually realize this is the hth term of the softmax. So the derivative of the ith term of softmax with respect to the hth term of the argument is just the ith term of the softmax times identity ih minus the hth term of the softmax, which is a pretty convenient result that will help us a lot when we actually do this differentiation. Okay, great. So now we're going to take the gradient of our objective function, but we're taking the gradient with respect to some wj vector, right? The w is now a matrix, not just a vector. So we're just taking the gradient with respect to the wj vector, which is the coefficients that correspond to predictions for the jth class. So let's go ahead and do that. Again, we can just ignore the sums because we're taking a gradient. And then y sub ni has no dependence on wj, so we pull that out. The log turns into 1 over softmax. Then we take the derivative of softmax, which we did earlier, and that gives us this. And then the gradient of wtxn with respect to wj is just xn. Technically, you're multiplying a vector of softmax derivatives with a matrix of zeros and xn's, but it'll just come out to this result. And now we see that these two softmaxes will cancel, so we can simplify to this. And then we see that this first term here is the sum of y n I ij from I equals 1 to k. But ij is only going to be equal to 1 when I is equal to j, and the rest of the time it will be equal to 0. So that means that the only term in sum from I equals 1 to k of yn ij that's going to be non-zero is when j equals I. So this thing just equals y sub nj. So we go ahead and we evaluate that, and then that gives us this line right here. And so now we want to evaluate this second sum right here. And we'll see that y is a one-hot vector, right? So it's like a bunch of zeros, and it's only one once. So softmax wtxn is actually not dependent on I. So we can just pull that out. But then this becomes softmax of wtxn, the jth argument of that, times sum from I equals 1 to k of y and I. But y and if you sum up all the elements of a one-hot y vector, you just get 1. So this term just falls off, and we just get softmax. So that gives us our result here. Then again, we just flip these two things around and get rid of the negative on the front. And softmax of wtxn sub j, the jth argument of that, is just our prediction for how likely the nth element, the nth data point is to be in class J, right? Because softmax, the way we predict is we just take the softmax of wtxn right here, and so the jth argument will just give us the probability that yn equals j. So really we're taking again, we'll use the hat here to represent predicted value. So this is our predicted likelihood of the nth data point being in the jth class minus the actual true 1 if it is in that, and 0 otherwise. And so we get a very similar result. Again, we get that the gradient is the kind of weighted average over all the data points, weighted by kind of like the error, like how far they are off. And so again, if we wanted to optimize this, we'd probably use a numerical technique like gradient descent or stochastic gradient descent, so we could use this gradient to find the correct W value.